This is Visual LLM. Will robots take my job? So hopefully you're in the right room where you want to be. So happy to have you here. You're hanging in there, so good for you. Just 2 more breakouts and then our closing remarks, so you're getting a lot out of this day. So I'm going to leave it over to our panel to start the discussion. This panel is led by Luigi Corte, and we also have Aaron Tan and Sina Karimi. So welcome them and enjoy the presentation.
Thank you very much for that introduction. So first, I'll challenge everyone here to give us your undivided attention. I'll also challenge you to not look at your phone, not look at your laptop. I want a fully captive audience. I actually think what we're showing here is going to be very important, probably in retrospect in the next 10, 20 years or so. I don't think anyone really foresaw what generative AI has done to white-collar work, right? Raise your hand if you use ChatGPT. It's a lot of people. Raise your hand if you were skeptical that it could write poetry, write art, do any of these things. I think a lot of people were in the camp of, oh, my job is safe, right? So the next frontier of AI is really not just through the API on our computer in a text-based interface. It's really humanoids interacting with the world. And I think one place that's very susceptible to this type of disruption is the construction site. The backdrop, obviously, is that we have a labor shortage, okay? And robots are already here, as Sina will show us. So really, I have a really short job today. I'm gonna make the introduction and pass it to the people who know what they're talking about, not me. So I'm Luigi Corte, CEO of Provision AI Software for Contracts. Sina Karimi is lead R&D at Pomerleau, Axlab Innovations. And we have Aaron Tan, who's CEO of Syncere AI and is a PhD candidate at the University of Toronto. The context here is, like I'll show you here, on August 6th, Figure, a software and robotics company, launched Figure 2, the next iteration of the humanoid robot. It's being piloted at BMW to supplement line workers. So we actually have robots currently helping humans in the factory, right? Humanoid robots. We obviously have had robots for a while, but now it's actually humanoid robots. Meanwhile, for example, the welding industry is projected to be short by 400,000 welders in 2024. So what we're going to be talking about today is what are the current use cases for robotics on site? What are the technical limitations from that increasing? And then what do those solutions most likely look like? Okay, so I'm going to pass it over to Sina to introduce himself and then to start the conversation.
Thank you, Luigi. I'm Sina. I'm R&D lead at Pomerleau. I'm with the innovation department, Axlab, which stands for our acceleration lab. I'm leading the team of tech experts, including robotics, AI, IoT. And today, I'm very happy to be part of this panel.
You can continue.
All right. So I'm going to start with construction managers and robotics, and what are the applications that we are seeing in terms of using robots on job sites. The first thing that we should always ask ourselves is that why should we even consider robots? Why robots, and why not just going, the way that we have been working so far? Always, the same answer is the labor shortage. Luigi just mentioned that, some stats about how we are short to find skilled workers on our job sites, and this is going to become a challenge in near future, in very foreseeable future. The second point is about the value-added task. We don't want to give a type of task that doesn't bring so much value to our company, to our people who are very busy on job sites. We can always ask some robots to take on the work that doesn't require creativity or human decision-making. That's something that has been proven in other industries, such as automotive industry. Why not in construction? Above all, worker safety. We don't want to give a kind of job that is dangerous or somehow not safe to our workers. The robots can take that kind of responsibility, and humans can be there to operate the robot first, so we are not taking the humans out of the loop, and also providing a safer environment for our workers on site. Plus, it's a robot, it's very cool, it's attractive. for our workers on site. And also, there are some other limitations. Some argue that we can always use fixed sensors, that's for sure. But if we can have one sensor on a robotic platform that can move around and collect the same data, why not? That's why having multiple sensors on our job site is one of the limitations, and this is basically due to high cost. And there are multiple benefits for construction managers, or also known as builders. They can quantify, analyze the progress. They can have a baseline for progress tracking and quality control. And at the end, they can monitor and coordinate workers on the site. When we are talking about robots, we always need to consider what type of robot fits our sites. There are multiple factors. First of all, we want to have comprehensive site visibility. How is that achievable? Maybe if we can ask someone to take a laser scanner with them or a camera and go to a large job site, it's going to take a while for them to capture the data. I have an example that on one of our construction sites, we had 200 columns that we needed to get the deviation from the columns, basically comparing reality versus what's been on our model. And it took a month to achieve that. That was a very time-consuming task. But with the robot, we were able to achieve that in 5 days. So we've seen a great ROI day, and I actually have ROI to share with you today in the coming slides. That being said, we want to go to a typical workflow of autonomous data collection. How does that look right now? And in the next, what are the limitations? First of all, we need to pre-plan on how a robot should navigate the job site. Construction sites are very dynamic, are ever-changing, and it could be difficult for a robot to understand where it has to go. So it has to be planned. The second step is about capture. The robot, when it's on its autonomous mission, it captures the data, and then it transfers. With that workflow, we are looking not only about capturing the data, but how we can transfer the data to the people who are analyzing them. That's how the robot can also provide the value of pushing the data to the cloud. People who are doing the analysis on the other side, they sometimes don't even know that there is a robot on the other side that they are getting the data from. All they know is that they are getting the data consistently, and that's how they can provide consistent value to our clients and our construction projects. And at the end, we have the software ecosystem. It's not always the robot that analyzes the data. The robot captures the low added value task, but then we have the people who are using the different software on the other hand to analyze and then provide insightful actions for our job sites. So when it comes to our to a construction project, we always need to understand what is the right tool for the right job. It could be a ground robot. It could be a drone. It could be a humanoid robot. It depends on what we want to achieve. So first of all, we want a dynamic mobile tool that can navigate around and collect data. Then we require high level of accuracy and tolerance. Type of project, very important. Since we are talking about frequent data collection, we need a type of robot that is repeatable, that has effective duration of autonomy, and it can be customized to different sensors, to laser scanners, to cameras, and maybe other IoT sensors down the road. So probably you've all seen Spot on social media. At Pomerleau, we currently own 2 Spot robots. We use the robots for site progress monitoring, quality assurance, and workers' health and safety. First of all, I misclicked that one. First of all, about the site progress. The robot captures the data from the site consistently. It's usually once a week, but it really depends on the job. Sometimes it's once a week, sometimes it's twice a week. What we want is consistent data collection. And that's what a machine or what a robot can achieve accurately. We all know that for AI analysis, we need consistent data, and we need the data that we are collecting on the job site to be collected at the same point, at the same location, with the same light conditions. With that, our downstream AI analysis works more effectively. And that's how we can bring quality data, and then we always talk about that, quality data in, quality data out. Quality assurance, that's something that a robot can provide insightful value to our construction sites based on what they are saying. And last but not least is the workers' health and safety. We don't want to risk a life when it comes to confined spaces on construction sites. There has been multiple examples on our construction site where we needed to monitor a confined space first before letting anyone to go in. And that's where a robot can play a key role. So about our journey, we started with 360 image capturing. We started small. It's always about change management and how we can bring that into our processes. We wanted to see that how a robot can achieve a simple task, such as 360 image capturing. We started small. We wanted to measure the ROI, and we provided the results to our higher management. Then we went with laser scanning. Laser scanning was our second use case where we integrated RTC 360, which is a product of Leica's, and we put it on spots bag for floor flatness and floor levelness analysis. We've seen very, very compatible results with the conventional methods. Down the road, we can see case study that we've done with the RTC 360. The picture on the left is captured using old school tripod, and the one on the right is the one that has been captured with spot. As you can see on the heat map here, they are very, very comparable. With that use case, we showed our team that a robot can capture as accurate data as a human can do. And again, it's not about replacing humans. It's about augmenting humans on the job site. Instead of taking tripod and doing the job, they can let the robot go and they can start working on something else in parallel. That's how we are always talking about improved quality on the job sites. So with that case study, first of all, we wanted to measure what is the ROI of that application. For that on-site mission planning, we have 15 minutes that we recorded the path for this bar robot. It's a one-time thing. It's repeatable, but first of all, we need to provide the navigation path to the robot. And then it required some on-site preparation time that includes, just turning on the robot, very simple tasks so that the robot can operate independently. With that regard, we've seen an improved quality of 95 minutes that is saved per week for a 1,100 square meter of job. That was a job that was in Ottawa that we were piloting in. And we saw that we've gained $12,000 per week. Again, it doesn't mean that if it's somebody else who is doing the job, they are paid like $20,000. It's about the improved productivity that we have gathered from our site. The next one is laser scanning BLK arc. There's actually one BLK arc in one of the booths. You can just pass by and see that. That provided a more seamless integration with Spot Robot on the job site. It was actually one of our job sites in Montreal where we piloted Spot with the BLK arc to collect data. And with that, we've seen that we were spending only 10 minutes, again, one time, 10-minute offsite mission planning based on our previously taken point cloud, and also we could have used our BIM. With that regard, we had 10 minutes that we spent for preparation time, and we saw 60 minutes saved per week for a 1,000 square meter job. That was a great productivity, and we saved like $7,200 per week on our construction site. And these were numbers from the direct ROI. There are some also indirect ROIs that the robotics can bring into construction sites. First of all is a remote control. We don't have to put a life at risk being out there in -20, -30, maybe -40, that they're collecting data. Instead of that, we can give it to a robot, and then that person can be responsible for operating the machine. Then it's also about seamless integration. When we collect the data with a robot, then it is also able to push the data directly to the cloud so that our downstream AI analysis can work more effectively, and also our people can have consistent data. It is a bit technical, but we are seeing improved machine learning results based on the data, since they are very consistent. Always the robot is at the same location, at the same time of day, with the same light condition. That contributes significantly to the analysis. And also we can say that we've had earlier error detection and also enhanced communication. With that point cloud that we've collected, we've seen that our subcontractors, they were able to catch their errors sooner rather than later. So the impact on our schedule was very, very slim. With that being said, robotics in construction is an evolving technology. It doesn't, I'm not here to say that robots are there today to do everything. There are limitations associated with the technology. First of all is the constant change of environment. In construction, today there is no wall, but tomorrow there might be multiple walls on the robot's path. How can we get the robot working in an ever-changing environment without interrupting too much? Because the goal here is to achieve autonomy, not just at every step of the way we just jump in and start interfering with the robot. Second of all is human-robot interaction. Based on what we've seen, it's a robot dog, it's cool. When it's on the job site, everybody takes picture and everybody is happy about it. But then when it becomes to actually working with the robot, we need that kind of human-robot interaction. We need to see that they are working alongside each other. It's not that, the robot is working, so I'm going to stop my work, I'm going to pause, and then I'm going to let the robot continue until the task is completed. That's not what we want. We are always looking for ways so that humans and machine can have that kind of perception to integrate and collaborate. And then it's semantic navigation. Maybe it's a new term, but we don't want to be very deeply involved in robotic concepts and robotic kind of navigation. We're a construction company. We're working with construction people, probably with no programming background. So we want them to be able to say, okay, I have this need, go to room A and do this task. That's something that has not been achieved yet. And also it's also about integration with other construction technologies such as BIM, GIS, and also there is more. There's always this domain is evolving, and we need that kind of integration so that we have one integrated system that we can leverage. These are the limitations that I'm seeing, Luigi, so far on the construction site, and I believe that these are the things that in an academia or in R&D side of things, they can help us in achieving a more productive construction sites.
Thank you, Sina. So what we see, at least in this presentation from Sina, is that there is ROI. And once you have ROI, it's like gravity. It's a force of its own. So the real limitations that we're seeing here are, number one, this is a robot dog. It doesn't have manipulators. It can't grab things. It can't, screw in something. That's one. It's the form factor of the robot. Two, there's some legitimate challenges here with interaction, right? So Sina was talking about one of the things that takes away from ROI is we have to set up the path. And that takes 10, 20 minutes each time you run Spot. So that's another technical limitation. Sina, if you were to talk about some of the other kind of low-hanging fruit things that you think could be automated on site, does anything come to mind?
I think the first that comes to my mind is about how we can make the robot understand the scene. How, come into a common perception of the environment.
Okay. What does that do for Pomerleau and the ROI of the program?
If we can have that kind of technology working and integrated on our job site, we can see much higher ROI so that most probably we can adopt more robots on construction sites. Not only Spot robots, but different type of robots trying to achieve different tasks. That's something that means for us so that we can invest more in that domain.
Perfect. Well, it's clear that the current limitation, or at least one of them, is the actual way you interact with the robot and you have it understand its context. Thank goodness we have a PhD candidate who studies this to tell us how it's going to be solved. Aaron.
Thank you. Can you guys hear me?
Yes.
Okay. All right. So, no, that was a great summary of the limitations. So a little bit about myself. I've spent the last 5 years working on a PhD at the University of Toronto, where I and my lab mates have been building algorithms to essentially help these generative AI models learn more efficiently. We're looking to basically defend this month and hopefully transition more into a startup building in this space. So today I'm here to sort of give a general talk about just generative AI in general, what they do, how do they work, what are their current limitations, and what we can expect them to get better at in the coming, say, 5 to 10 years. So to directly answer,
Excuse us for 1 second.
It's going there, but not here.
Oh, it's going there. Okay, interesting. Okay, maybe I'll get up here then, so I can see.
Here, let me just go back.
Okay. There we go. So maybe I'll get up here so I can kind of see what I'm talking about. So generative AI, I'm sure, from the beginning of the talk, you guys are all familiar with generative AI, ChatGPT being one of the most famous ones. And we think that ChatGPT is something like a ChatGPT can have the potential to address these limitations essentially directly, right? So the first thing is that to deal with constant changes of the environment, generative AI is naturally suited for that task because they're trained on massive data sets and they can generalize across varying environments in brand new novel conditions, right? In terms of human-robot interaction, generative AI also does a pretty good job at understanding language. It's able to hold a conversation with a human being. And that's something that we can definitely try to leverage in robotics to try to improve that interaction with robots. In terms of semantic navigation, the other thing that generative AI is great at, because it's trained on so much data, is that it has great common sense knowledge. It has a large pool of data that it could sort of almost refer to during test time. And that makes it well suited to address these type of tasks. And lastly, generative AI also is well positioned to learn from large sums of data, right? So with contact applications out there, there's an opportunity here for generative AI to also sort of learn from these data and build new skills. So before I go too further deep with how generative AI can be applied to robotics, I want to give just like a sort of general introduction and tutorial about what generative AI is and how they're built and trained, right? So in general, or I guess at the high level, generative AI describe these large general purpose models. And large typically means two things in this context. It's large in the data set that it's trained in, and large in the model architecture. So that's literally the size, the pure number of parameters that exist inside these models. And as we know now, these things are quite good at generating text. A lot of us, I'm sure, have used them to write maybe an email, a birthday card. My personal favorite one is actually getting them to code. It's very, very effective in that sense. And there's a few options out there right now. So OpenAI's GPT is the most popular one, but we have Anthropic's Cloud, there's Gemini, and Apple is releasing their own, I think, this fall. So how is generative AI different than all the AIs that we've been hearing about for like the past decade or two, right? And to quickly sort of place generative AI, this is the example that I like to give. So traditionally, on the most far left of the screen, developers and engineers sort of work with these rule-based systems where the idea is that you would design sort of these conditions where if the condition is true, then you execute some sort of predefined task. So this works well if the developer is able to sort of imagine all types of possible scenarios. When conditions that happen outside of these scenarios, then it could get a little bit tricky. And with robotics in the real world, as we know, the real world environment is quite dynamic, quite random. A lot of things can happen. So oftentimes it's not very easy to actually plan for every possible scenarios. So that sort of pushed us towards these data-driven systems in the stage number 2 here. And this is your classical neural networks, right? So this is giving a large amount of data with some labels for these data. How do we learn from this data and reproduce what is learned in the data? So these type of networks sort of are very common, sort of exist in almost every application that you're using now. One that I like to discuss is, for example, when you take a photo on your phone is already sort of looking at, let's make the sky a little bit bluer, let's make the grass a little greener, because based on its training data from social media and whatever, it knows that these are the certain characteristics of that image that people care about. So let's make them better automatically already, right? So then that brings us to the third stage, which I think is the most popular, exciting technology currently, and I expect it to be the most popular and exciting technology over the next decade, and that's generative AI. So instead of just learning from data set and reproducing what's in that data set, generative AI essentially are just neural networks, but scaled way up. And we call these architectures transformers, maybe you've heard of them, or diffusion models. And these architectures can learn from very, very large amount of data. We call them internet scale data. Essentially, all the texts, all the videos, all the images that you could find on Google can be used to train these models. And as a result of it training from such a large model, it's able to sort of generate brand new data that's within the same distribution of its data set, right? So that's sort of places where generative AI is currently. And here's a quick slide about like sort of how is it predicting text? How is it generating text? So I came up with this little graphic here. And essentially, given a large amount of text, let's say the entire encyclopedia, right? And let's say there's a sentence that's like, the weather is nice, I should wear shorts. What are these transformer architectures? What are these language models really actually learning? Well, the answer to that is that they're learning the correlation between every word in that sentence with every other word in the same sentence. So the blue lines that you see here, the darker the blue, the higher the correlation. The lighter the blue, the lower the correlation. So in a sentence that's like, the weather is nice, I should wear shorts, you can expect that the word weather has a higher correlation with nice, which then has a higher correlation with the word shorts, because, semantically you're wearing shorts because the weather is nice, right? So by basically training these transformer models, these large language models essentially, on this gigantic text data set, we can essentially teach these AIs to understand the syntactic and semantic structure of basically human language. And it's able to sort of understand what words play well with other words and how should we piece the sentences sort of together. So then when you're using ChatGPT, what's essentially happening is that you type in your question on ChatGPT, maybe you ask a question like, what is the color of the sky? What it's essentially doing in the back end is that given this input, what is probabilistically the highest, most likelihood word that would appear after the words you just put in, right? So in the case here, I sort of illustrated based on the previous training sample per se. The weather is nice, I should. The LLM in its backend is sort of trying to guess what the next word should be. But because of its data set, it see that the word where has a 70% probability of being the next word compared to have or go or keep, right? So this itself is probably the main strength of LLMs, but it also happens to be one of its main weaknesses. So the strength here is that it's great at picking up words and forming complete sentences that make sense. But the bad thing about this is that it's only doing next word prediction, meaning that the LLM itself doesn't actually have awareness of the concepts within these sentences. All it's doing is that, probabilistically speaking, given these set of words, these are the most likely next sequence of words. And this is what can lead to sometimes what we refer to as hallucinations, where you should not be able to rely on LLM for factual information because it could just hallucinate because it's sort of averaging over all this data that it's seen in the past. But in most of the general use cases, such as paraphrasing or rewriting your emails in a nicer tone or whatever it is, like it does a pretty good job in that sense. So how are visual large language models different than large language models per se? Well, the thing here is that they're mostly the same. Behind the scenes, there's some engineering things that has to happen for them to sort of account for different types of modalities. And by modality, I mean like text, image, audio, video. I think soon, I think the researchers should start working on maybe smell, maybe touch. All these are type of sensory inputs that as humans, we can process really well. And the only difference between a visual large language model versus a large language model is that you could train these sort of encoder decoders that sort of brings, all this text, audio, image into the same kind of representation space from the perspective of the LLM. So it doesn't have to distinguish what's what. And then once it's generated as output, we train a decoder to then decode that information back to their original formats. But behind the scenes, it's still doing that sort of next token prediction based on what it's learned. Okay, so that was sort of what generative AI is, what large language models are, and how visual large language models are any different. Now we can talk about how I think they could be used for robotics. So 2 things. One thing is that I think they could be great for robot perception, meaning they could be great at, given an image, describe in detail what's inside this image, right? So that's understanding. I think Sina touched up a little bit on that too with sort of changing environments and understanding, what's going on in the scene. The second thing is robot reasoning and planning. And that's basically given a task, like a global task, like, for example, how to make sushi or something. LLMs are also great at breaking that main task into subtasks because of its common sense knowledge, essentially. So because it has the ability to decompose big tasks into subtasks, that makes it great at reasoning and planning for these more complex tasks that we want the robots to do. So overall, I think those are the 2 areas where generative AI could be useful for robotics. Then the question becomes, how do we actually use them, right? How should we leverage them? And similarly to your usage with ChatGPT, it's through textual prompting or visual prompting. And these are sort of like the 2, I guess, for sort of frontiers, state-of-the-art techniques that people are using in papers published in the last 3 to 4 months on this topic. So for textual prompting, it's just text in, text out. For visual prompting, it's image in, maybe text out. So I'll show some videos here. This is an example of a paper published by Google DeepMind in Berkeley where the task here is we want the robot to go find an oven. And what's happening in the back end is that the robot is using its camera to see an image of the scene of someone's house. And it's basically sending it to ChatGPT and be like, I'm looking for an oven. What should I do next? ChatGPT, because it can understand images, it says, it looks like there's a kitchen in front of you. And through my own common sense knowledge, I know that ovens typically appear in kitchens. So I think you should navigate forward a little bit and then get another image and let me tell you what to do next. So you could almost imagine this as like ChatGPT on wheels, essentially. And this gives it great great ability to be able to generalize to all types of environments. For example, ChatGPT isn't necessarily trained in this person's house, isn't trained in this particular office, but because these environments look like data that it's seen before, it's able to generalize directly without actually having to train in that environment. And that's probably one of the more powerful properties of using generative AI for robotics. Another example is through visual prompting. So what people at Google also realized is that instead of just passing the raw image in, let's add some markers to the image. So in this case, on the bottom left there, you could see that basically the image comes in, and what they do is they add these circles with numbers in them, overlay them on top of the image, and label them 1, 2, 3, 4, 5, 6, 7, 8, 9, basically. And we asked ChatGPT, hey, if I'm trying to go into this room, which number in the image should I go towards? So by putting a marker in the image, it now makes that reasoning decision for the VLM more explicit, right? Oh. But yeah, I guess I can't play the other video on the right side, but essentially it's the same idea. By overlaying some visual prompt on the image, it makes the VLM's reasoning basically better instead of passing in a raw image. And that's kind of the more exciting areas that's happening right now in terms of research for how to use generative AI for robotics. And then I'll finish quickly here with just essentially like where I see sort of like the future of robotics and what are the current limitations, right? So as I've sort of alluded to during this talk is that all the approaches that you've seen before this is basically engineers and researchers trying to almost retrofit something like a ChatGPT for robotics reasons, for robotics applications. But the problem here is that ChatGPT isn't designed with robotics in mind, right? It's designed on 2D images and text from the internet, right? But robotics need 3D understanding of the environment in order to function properly. So by default, ChatGPT does not have 3D understanding of the environment. It's never seen depth data, it's never seen LiDAR data before, only images and text. And researchers sort of are currently trying to sidestep this problem by coming up with creative ways to prompt the model so that it can still get it to sort of generate some output. So the image, and this is further sort of demonstrated here in this video, where in the top right corner, you can see this is Tesla's latest work on their humanoid robot called Optimus. And they're demonstrating that this robot can do this pick and place task really well. But the thing is, to train that model is actually what you see in the bottom right, where they have several operators wearing VR headsets to be able to track their hands doing the exact same task. And that's one of the main problems, which is that you need to be able to collect these kind of like motion data in order to complete this rather kind of simple task. So from what I see, the two main challenges going forward, I guess, is basically the abundance of data. You need a lot of data for it to really be ChatGPT designed from the ground up for robotics. And the second thing is, which is something that I've been working on for my PhD, is how to learn efficiently. So say in the case that we just can't scale up our data as fast as possible, right? Because robotics data isn't exactly like text and images that people freely offer on the internet. The other way to approach the same problem then is how do we build algorithms that can learn with less data? So that's sort of like the sort of, I guess, two challenges that I kind of see going forward from here on this topic. Yep, thank you.
Thank you, Aaron. So I think what we've seen is a couple things. One, we see that there's real ROI of using robots on site, but it's limited by current technical constraints. And what Aaron's demonstrated is that we're actually making breakthroughs on those technical constraints. So the kind of overarching question of this talk is, will robots replace us on site? The answer is probably yes, in some form, but to what degree? So I think that we'll leave it there. I'd love to get some questions from the audience for both Aaron and Sina, both from a theoretical and from a practical perspective on robots. Thank you so much. Let's give it up for the talk, for the speakers. Thank you. Any questions?
For Sina, talk about ROI. We'll switch that up to time to value. Like from when you guys started looking at the spot dog, when do you actually see that time to value? What the time journey look like?
So the question is time to value. What did that look like for Pomerleau?
Time to value when Spot becomes profitable, when we are having the on-job sites.
Your journey of when you actually saw it getting some traction. starting to look at it to like, wow, this thing's really, giving us some good data?
Yep. I have to take a flashback to 2019 when we had spotted Pomerleau. At first, there was a lot of excitement about having a robot on job site. We first started with small tests, and after a couple of years, we understood that Spot pays for itself after 2 years. That's what we've seen. This is. At first, there was a lot of try and error because we needed to understand how the robot works. We needed to provide some feedback, to Boston Dynamics to address the limitations. For example, when the Spot was going upstairs, it was falling down all the way. So I was witnessing Spot going down the stairs from I think 20 stairs, but it's designed to take that. So we weren't worried about all those, but it took some time to provide the feedback to Boston Dynamics, who are the manufacturer, and they kind of worked on the limitations, and they provided us with updates, and they really actually improved based on the feedback we provided them. So yeah, that was the long answer. The short answer is 2 years, and after that we are seeing the real ROI on our job sites.
Hi, my name is Harsh Raval. I am a BIM intern at Pinnacle Infotech. I have a question in the form of a suggestion to Aaron. As he said that the AI is not completely ready yet, so it lacks a lot of data. So what if, in terms of BIM or in terms of construction, for example, in Revit we have lots of plugins we add on. Revit is a basic platform given by Autodesk, and then we add different plugins to it. Similarly, is it possible, or maybe in future, that we have a specific criteria, maybe for architecture, or maybe construction, maybe production line, we just add it to the AI platform for a specific category, and that works on as a support to the robotics or the AI?
Are you asking if it's possible to fine-tune smaller AIs per subtask? Is that what you're saying?
Yes.
Yeah, so I think fine-tuning refers to the concept of, for those who are not aware, is basically, it's very expensive to run these really large models. You have to pay the API cost, but to be honest, not every task requires sort of this general knowledge. Sometimes you could just actually train a specific AI for a specific task, and then you wouldn't have to pay. So the answer to that question is yes. I think actually that is, what the industry trends towards. They want AI models to become smaller so that they can run on sort of embedded systems and not over the cloud. This also makes them, more secure and private, because you're not then passing your information to someone else to handle the processing. You could just operate it yourself. So I think collecting the data, setting up the infrastructure to collect this kind of data, and then training these smaller models is definitely the path forward.
Right. And to add on, is there anything currently, any platform that has done this thing in a shorter level, in a smaller level?
I'm familiar with some startups building in the space of maybe for digital applications. I'm not too familiar with if there's any within the construction space right now.
Right. Thank you.
No problem.
Thank you for the question. Any last questions? Yes.
Question for, so we saw that Spot can do the scan of what other one-on application methods it does that you saw was very successful with running everything? We got a lot of positive feedback on construction site.
That's a great question. We've been exploring the ways of integration of IoT sensors with Spot, namely gas sensors, before sending anyone in. So we've had Spot go in and then communicate through a remote connection platform that we have in-house. And with that, we were able to collect the data before sending anyone in. That was the first one. The second one is also about again IoT sensors, mostly about dust and noise sensors. So instead of having multiple sensors around the job site, we had only one on Spot's back, and it was going in different rooms to collect that information. One other thing that we've seen, and we are working on that, multiple type of data collection at the same time. So we can put a laser scanner on a spot back. We can put a 360 image, 360 camera on a spot back. We can add sensors, and recently, we wanted to have GPS as well. So with all that information, we are going out only one time, but we are collecting multiple types of data.
Okay, I think we're at time. Thank you so much to our speakers. Give it up for them. Thank you for the question.